Hello everyone, Math 2 students. We're going to be finishing up lesson 613, which we started in class on Thursday or Friday, March 4th or 5th, depending on which class you're in. So we're going to continue with that, and we got through a lot of this in class, but we didn't finish, and I'm not sure how far we got, but we're going to start with the Pythagorean identity, having gone through a couple of examples. So on this slide, and we may have done this class, we may not have. So I'm assuming we did a little, but we're going to continue with it. So we know that sine theta of some angle, quantity squared, plus cosine of that same angle, quantity squared, equal to 1. This is often abbreviated like this. I don't like this abbreviation, even though I use it, and I'm very fond of it. Sine squared theta plus cosine squared theta equals 1. Because it looks like we're squaring sine, which we're not doing. We are squaring the value of the sine of theta, whatever that fraction is, and then squaring it. And so it's important that we kind of understand that even though that looks like we're squaring sine, then the angle, we're squaring the result of sine theta. Okay, so the ratio of sine at the angle. Okay, so that's what the Pythagorean identity is. We've done a couple of examples. We're going to try to see if we can prove that this is always true. And again, we may have gotten through this in class, we may not have. I'm not sure which. So we're just going to assume that we didn't, is actually what we're assuming. So testing examples we did in 626C can give you an idea whether a statement is usually true, but whether it's always true, we need to prove a general case. Sometimes it helps to start with a theorem that we've already proven. So first of all, we're going to find sine A equals all of these of this triangle right here. So we're talking about A. Down here, we're not going to be using orange anymore. And if my pen went white, there we go. So A, so sine of A is A lowercase a over c. Cosine of A is lowercase b over c. Tangent of A is a over b. And we'll need those as we go forward today. So that's no big deal, pretty straightforward. And then sine of b. So we'll do that, those in blue. The sine of b, so now I'm talking about this angle, opposite. Oh, I should have done that. SOHCAHTOA, sorry. So sine of b, lowercase b over a. Cosine of b is a over b. A over. Start over. SOHCAHTOA. Starting over. Sine of b is the opposite side over the hypotenuse. So lowercase b over c. Cosine of b is the adjacent side over the hypotenuse, or a over c. Tangent of b is the opposite side over the adjacent side, so b over a. Okay, so the idea is we have both of these. We're going to use these to help us as we go forward. Okay, so kind of take this picture in your head and bring it with us. We're going to use it as we go through the next set of problems to help us figure out what's going on. Okay, so again, it said sometimes it helps to start. Write an equation about the side lengths of ABC. So what do we already know? Well, that would be, we already know Pythagorean theorem. And we've been using it quite a bit the last days. And so the Pythagorean theorem says that a squared plus b squared equals c squared. So we already know that. Okay, so we're going to use that to help us again. No big deal on this slide. So let's see what's going on if we move to a more general form. So, whoops, sorry, one too many. That's good. Good to know. So now we're going to prove that the sine of theta squared is equal to the cosine of theta squared. So theta, remember, is angle A. So the first thing we're going to do is write this down with what we know. So sine of A, or theta, is A over C. And we're going to square that. Plus cosine of theta is b over c, adjacent over hypotenuse squared. And we're trying to show that it is 1. Okay, so let's just go ahead and square this. It's a squared over c squared plus b squared over c squared equals 1. So that's a squared plus b squared. Since the denominators are the same, we can add them together. Over c squared is 1. Now, I am tempted every time I do this derivation to multiply both sides by c and just say, oh, look, Pythagorean theorem, all done. But that assumes that they're already true, and we're trying to show that they're true. We can't assume that they're true. So this part is really weird and always bugs me. Pythagorean theorem says this: a squared plus b squared equals c squared. So that means I can replace c squared with a squared plus b squared. So I can substitute. And so a squared plus b squared, the one I already had, so I should have written it in red. And c squared can be replaced with a squared plus b squared. And anything divided by itself is 1, and so that's why it's equal to 1. I should take this dividing off. And let's use a brighter color over here. Equals 1. Okay, and so that's because I replace c squared with the Pythagorean theorem. And so, yes, we could clearly show the Pythagorean theorem happens, and I like that better. But this is more mathematically correct because we didn't assume they were equal. If we multiply both sides by c squared, we're assuming the equality. We're trying to show the equality. It's a technicality. Okay. So, in other words, since I did it with all letters, I know it's always true. Isn't that cool? All letters means it's always true. It's a very, very interesting set of information. Okay. So let's go to the next slide. So now prove this statement, that the sine of theta divided by the cosine of theta is equal to the tangent of theta. And so before we do any of that, let's just write them down. Sine theta. We already have them on the other page, but I'm not there anymore. Sine theta is opposite over hypotenuse, A over C. Cosine theta is adjacent over hypotenuse. And by the way, this is where I think we didn't get, so I'm going to start slowing down a little bit. If we got somewhere, we got to the previous example, but not here. Then tangent theta is equal to opposite over adjacent, so A over B. So I'm trying to show that if I divide these two fractions, I'm going to get A over B. So let's go ahead and just do that. We're going to divide A over C by B over C. And this long line just means divide, right? So I'm going to rewrite that mathematically. And when I divide by a fraction, I really multiply by the reciprocal. So A over C is multiplied by C over B. So then I end up with A times C over C times B. The C's cancel out because C divided by C is 1. And so A over B, which happens to be tangent. So yeah, that's true. Okay, so that one's a little weirder. It's fractions and it makes us uncomfortable. And so they're all fractions because, sorry to say, sine, cosine, always a fraction. Always less than 1 unless something weird is happening. Sine of theta and cosine of theta are fractions. Smaller than 1, always, because C is always the largest because it's the hypotenuse. And that does not change even when we get into crazier versions of sine and cosine. Tangent, however, can be bigger than 1. It's a little weird because A divided by B, if A is larger, it's going to be larger. Okay? So tangent can be bigger than 1, but sine and cosine are always less than 1, but bigger than negative 1. Or equal. Can be equal. All right. So that's that. Okay? So again, what I did is I took my values, sine, cosine, tangent, and I wrote the fraction with them in it. Then I remembered that, hey, a fraction line just means division, so I rewrote it as A over C divided by B over C, which is the same as A over C times C over B. Then A times C on top and C times B on bottom. The C's cancel to make 1. And I'm left with A over B, which is the tangent of theta. So I demonstrated that sine of theta divided by cosine theta is tangent theta. Okay? All right, moving on. So let's try something. Theta is acute angle in a right triangle DEF. If you know that the cosine of theta is 9 over 41, can you find the sine of theta? So, here's a triangle. This is, we're going to let this be theta, just because the way I drew the picture. So, wait, no, I was right the first time. Cosine is adjacent over hypotenuse. So 9 over 41. Adjacent over hypotenuse. And then we have to find the missing side of this right triangle. And I can do the Pythagorean theorem to figure it out. Or I can remember that when we were playing with triples the other day, we know the answer here. The answer is 40. I'm going to do the Pythagorean theorem to back it up. I'm going to have 41 squared minus 9 squared equals the unknown side, which we're going to call O. We're not going to call O. We're going to call P for opposite, P squared. And so that's 1681 minus 81, 1600. And so square root of 1600 is 40. Okay. So what's the sine of theta? So sine of theta must then be 40 over 41. Okay. The other thing we could have done is rewritten it as cosine squared plus sine squared. Cosine of theta squared plus sine of theta squared equals 1, and figured out what it was there. That's harder. I find this way is easier. Okay. So there's that. Let's try it again. Oh, it's just walking us through it. Okay. All right. Never mind. So there's that. What do we know about the side lengths of DEF? So, given that I had a triangle in the previous thing, what I know about the side lengths is that they will fulfill the Pythagorean theorem. I think it expected me again to do that another way. So I can find the side lengths by doing that. Okay. I think it was expecting me to use sine squared plus cosine squared. I just didn't. Sorry, guys. All right. So then, when I get to this side, C, find tangent. So now that I have that, tangent of theta will equal opposite over adjacent. And that's that. That's all there is to it. Okay. And that's it. That's the end of our slides. Hope you have a great day. We will see you guys soon.